Hi, today we are going to speak about the Bernoulli's principle and the derivation of Bernoulli's principle. Let's initially derive the Bernoulli's principle. In order to derive Bernoulli's principle, let's draw a diagram. This is a pipe which is inclined and it is of varying area of cross section. That means it is having two different area of cross section. Let's say the area of cross section over here it is A1 and the area of cross section over here is A2. The liquid is flowing with a velocity v1 through this region, and assume that liquid is flowing through a velocity v2 through the other region. Then in a small interval of time, a molecule over here, it will travel a distance of this much and it will reach at this point. This distance traveled, we could write it as v1t. It's because we could write velocity is equal to displacement by time. Therefore, we could write displacement is equal to velocity into time, and this velocity is v1. That's why we are writing this distance as v1t. Similarly, the molecule which is over here, in that same time it will travel a distance of, let's say, this much, and let me write this distance as, I am writing it as v2t. Then the pipe is aligned in an inclined manner, so that let this be our surface. The first portion of the liquid that we are considering, it is at a height h1, and the second portion of the liquid that we are considering over here, it is at a height h2. This is v2 h2. Then we are going to find out the net work done in this process, and by work energy theorem we know work done is equal to change in kinetic energy plus change in potential energy. The total work done is equal to change in kinetic energy plus change in potential energy. Then what is change in kinetic energy? We could write change in kinetic energy as final kinetic energy minus initial kinetic energy, and or the kinetic energy over here, we know the expression for kinetic energy is half mv square. The kinetic energy over here, it will be half m2 v2 square, and the kinetic energy over here, it would be half m1 v1 square. The change in kinetic energy, I'm writing it like this: half m2 v2 square minus half m1 v1 square. Then according to the law of conservation of mass, the mass of liquid which is flowing through the first section, it should be equal to the mass of liquid flowing through the second section. Therefore, I could write m1 is equal to m2, and if m1 is equal to m2, we could write m1 by 2 into v2 square minus v1 square. I am writing it like this since m2 and m1 both are equal. Then let's move for the change in potential energy. Change in potential energy, as we know, the expression for gravitation potential energy is mgh. Since h2 is greater than h1, the change in potential energy will be the potential energy over here minus the potential energy over here, that is m2gh2 minus m1gh1. By using this concept, that is m1 is equal to m2, we could write m1g into h2 minus h1. Then instead of this work, I could substitute it like this, that is work is equal to m1 by 2 into v2 square minus v1 square plus m1g into h2 minus h1. Then as I could write, that is, we know density is equal to mass by volume. Therefore, mass is equal to density into volume. And by using this concept, we could write m1 is equal to density into volume of this portion. Volume of this portion will be the area of cross section into distance. That is, volume will be area of cross section A1 into distances V1t. Therefore, m1 can be replaced as rho A1 V1t. Then, if I am taking m1 common out of this equation, I could write m1 into, expanding the bracket, v2 square by 2 minus v1 square by 2 plus taken outside, that is m1 is taken out, then expanding the bracket, gh2 minus gh1. Clear? Then replacing for m1, rho a1 v1t into v2 square by 2 minus v1 square by 2 plus gh2 minus gh1. Clear? That is work done. Then next I am going to find out work done in another norms. That is, if I am going to find out the net work done in this process, it will be, since it is inclined in this direction, we will be pushing the water in this direction, so that the work done over here will be little bit greater than the work done over here. Then the net work done between this process will be, it will be W1 minus W2, because gravity will pull it downwards. W1 minus W2. As we know, the expression for work is W is equal to F dot X, and in this case we could write W1. Then what is W1? W1, it would be, oh, let me write W is equal to, instead of this W1, I will have to write F1 into displacement. What is the displacement in this case? It's V1. And instead of this W2, we will have to write F2 into the displacement over here. It is V2. Then we know pressure is equal to force per unit area. As we know, pressure is force per unit area. Force can be written as pressure into area. If I am using this concept over here, this F1, I could replace it as, F1 can be replaced as P1A1, then V1T as such, minus F2 can be replaced as P2A2, then we'll write V2. Then let's recall the equation of continuity. What equation of continuity is saying? The mathematical form was A1 V1 is equal to A2 V2. This was the mathematical form of equation of continuity. Area of cross section, velocity, the product of area cross section and velocity will be constant. Therefore, A1 V1 equal to A2 V2 means we could take from these two terms A1 V1 T common out, then it is P1 minus P2. W is equal to A1 V1 T into P1 minus P2. Why? Because A1 V1 is equal to A2 V2. T is already same. Then let's take this equation as equation number 1 and this as equation number 2. Equating 1 and 2, we could write rho A1 V1 T into V2 square by 2 minus V1 square by 2 plus GH2 minus GH1 is equal to A1 V1 T into P1 minus P2. We could cancel this A1 V1T and this A1 V1T. Therefore, then if we are expanding this, and while expanding this I am taking the terms which is having 1 to this side and the terms which is having 2 to this side. That is rho, let me write it over here, rho V2 square by 2, I am retaining it in this side itself, and there will be rho V1 square by 2, I am taking it to the other side. That is in order to fix it in this paper I am writing it over here, rho, or let's write it over here, that is rho V2 square by 2, this minus rho V1 square by 2, I am writing it over here, minus rho V1 square by 2. Then there will be rho GH2, I am writing it over here, rho GH2. Then there will be a minus rho GH1, I am writing it over here, rho GH1. Then there will be minus P2 over here, and I am taking this minus P2 to the side, that is P2, and over here there will be a P1. Therefore, we are getting an equation like this. Can you see an equation like this? And this is our Bernoulli's principles basic equation. Let me write it over here. P2 plus half rho V2 square plus rho GH2 is equal to P1 plus half rho V1 square plus rho GH1. This equation is called as Bernoulli's principle, and if I am saying Bernoulli's principle, the total sum of pressure, this term I'll call it as kinetic energy per unit volume. Half rho V square is called as kinetic energy per unit volume, and this term I'll call it as potential energy per unit volume. That means the pressure, kinetic energy per unit volume, potential energy per unit volumes sum will be a constant, or I'll write it over here, P plus half rho V square plus rho GH is equal to a constant. This is our conclusion for Bernoulli's principle. Pressure plus kinetic energy per unit volume plus potential energy per unit volume should be a constant.